Acids and bases. Let's go through the acid and base topic here. Year 12, you already know how it is. Year 13, whatever. Yeah, let's pan that, yeah? Come on. Straight into it. So Bronsted-Lowry acids, yeah. Bronsted-Lowry acids are defined as proton donors, yeah. This is because when placed in water, they dissociate to form H plus ions, yeah. So and H plus ions is obviously a proton, yeah. So as you see, yeah, when you place like a strong acid like HCl in water, yeah, it breaks up. We call that dissociation, yeah, or ionization, yeah. And it breaks up into what? It breaks up into H plus, yeah, and Cl minus, yeah. So that's why we call it an acid, yeah, because it donates that proton, yeah. That H plus, yeah, has come from the HCl, yeah, and it's been separated. Do you see that? And then this H plus will then join water to form H3O plus. Yeah. So you think, how come it's become H3O plus? Well, think about it. You've got H2O and you're adding another H plus. That's gonna become H3O plus because the plus gets carried from the H plus. Yeah. So that's why we call it a proton donor. That's why we put acids proton donors. Yeah. It's because obviously here the H got donated from the HCl. Yeah. Onto the H2O. You get it? And obviously that's the situation there. H plus ions, yeah, they'll always form hydronium ions in water, yeah. So you're never gonna have just H plus inside water by itself, yeah. If you dissociate acid in water, the H plus ions will always join to the water to create hydronium, yeah. And that's actually what makes it acidic, innit? The thing that makes it an acid, yeah, is obviously the ability to donate a proton, yeah. That's what acidity is the ability to donate a proton. That's what makes it an acid, yeah. And so this hydronium ion that's in water now, after the dissociation of the acid, that has a spare proton if you think about it. It's H3O plus, yeah. That's got a spare proton that can easily be donated. So readily be donated, yeah. So obviously that's what makes the water actually acidic at that point. Here we got Bronson-Lowry base here. So a Bronson-Lowry base here is defined as proton acceptor, yeah. So why is that? Why is it a proton acceptor? Well, it's because when they react with water, they accept H plus ions and form OH minus ions. So as you see here, we got a B, yeah, that's base, yeah, that's what that stands for, yeah. And you're reacting that with H2O. If you react it with H2O, H2O is gonna act kind of like an acid. We said acid is a proton donor, yeah. So H2O is gonna give away a H plus, and that H plus is gonna attach to B, and you're going to be left with OH minus. And because B got a H plus attached to it, yeah, that therefore means that it's a proton acceptor. You see that because it accepted the proton, accepted the H plus here. And as you see, this is a reversible reaction. It's not really too likely to make the outcome here. You know what I'm saying? It's not likely for the proton to be accepted. There's no reason for it to be accepted, yeah. So therefore, there's obviously going to be a low concentration on the right hand side. Strong and weak here. So acids and bases can either be strong or weak. Yeah, a strong base or acid will dissociate or ionize completely in water. Yeah, whereas a weak base or acid dissociates or ionizes partially in water. Yeah, and often that can be represented by a reversible thing. Yeah, calm. Let's look at weak acids then, yeah? So here we've got ethanoic acid, yeah? CH3COOH. And as you see here, it's dissociating into H plus and CH3COO minus, yeah? This is the base model for all acids, by the way. It will dissociate into the H plus ion and then the rest of whatever that compound was, yeah? We call it like a conjugate, yeah? Alright, calm. So what I got on here, yeah? What's going on, yeah? Well, we got what? Like we got a weak acid here, yeah? The backwards reaction is favored, not a lot of yeah. So because the backwards reaction is favored, there's actually not a lot of H plus being produced. You understand? So there's a low concentration of H plus, low concentration of CH3COO minus, and there's a high concentration of CH3COOH. Why? Because it's barely dissociated. You get it? So that's what makes it a weak acid. You're not making a lot of H plus ions. That's what makes it weak. You get it? So examples of weak acids you need to memorize are carboxylic acids such as ethanoic acid, yeah, which is shown above. Calm. Strong acids, on the other hand, yeah, the forward reaction is strongly favored. So you can write this arrow here, you can write that as a reversible reaction if you want. But if you write that as a reversible reaction, yeah, or equilibrium, then you need to make like obviously this side and this side is going to be higher concentration than the right hand side. So effectively, it can just become like one single arrow going to the right because that's how strongly it's dissociating, yeah. So obviously, the forward reaction is strongly favored, and hence a high concentration of H plus is produced here. And some examples of strong acids you need to know about, yeah, is things like HCl, that's hydrochloric, H2SO4, that's sulfuric, and HNO3, that's nitric, yeah. Calm. Weak bases, yeah. So in a weak base, they don't dissociate much, yeah. So the backward reaction is strongly favored again. So again, we're not making too much NH4 here, and we're not making too much OH minus. You get it? And as you see here, yeah, NH3 doesn't even have. That's how much of a weak base it is, yeah. that it doesn't even have OH minus containing it. It doesn't even have a hydroxide group. My man's got to react with water, fam, in order to produce hydroxide ions, yeah? That's how deep it is, yeah? So obviously water here is acting as an acid again, effectively, and is donating one of its protons, yeah, to NH3, and that's gonna become NH4. So again, that's how much of a weak base this is. This reaction wouldn't really go down like that. You get me? You wouldn't really produce a high amount of OH minus ions afterwards, yeah? So that's why that's a weak base. And as you see, this is a strong base. Strong bases contain hydroxide, so there are often things like hydroxides, like sodium hydroxide, potassium hydroxide, stuff like that. By the way, another thing, yeah, with ammonia, yeah, anything that's like adjacent to ammonia as well, like anything that has like ammonia added to something is also going to be a weak acid, yeah. Just to identify if it's a weak acid, just look, does it have an OH group in it? That should be the first question, yeah. Alright, cool. Calm. So obviously the forward reaction here is strongly favored, yeah, and hence many OH are produced. Again, I've written this arrow as just a solid arrow instead of a reversible reaction. That's how strongly it's favored to the forward reaction, yeah. And obviously strong acids often already contain the OH, and so many hydroxides are strong acids. Yeah, calm. So NaOH here is just dissociating in water and aqueous solutions here to produce Na plus and OH minus ion, as alkalis or bases do. Calm. Acid-base reactions, yeah. So this is a very simple situation. You got an acid, which obviously got the H. Yeah, that's what acids contain. They always contain a H. And that H is going to be donated onto the base. That's what makes acid an acid. It's a proton donor. And then when the H attaches to the B, yeah, that's obviously what makes it a base in it. It's attracting, it's accepting the proton in it. So that's what you're getting here. You're getting the conjugate base and you're getting the conjugate acid in it effectively in a way, if you think about it. Because now that it's lost the H, the acid has effectively kind of become a base. Because if you think about it, it can easily, attract that again. It can easily attract the H plus again. And the base has effectively become acid because now it has a spare H plus. So that's how it works, yeah? Alright, calm. So let's look at water then, yeah? So water can act as both an acid and a base, yeah? We call that amphoteric properties, yeah? Amphoterism, yeah? So when acid is added to water, it acts as a base and it accepts a proton. So if you add acid to water, the water's gonna act as a base, yeah? So as you see, the H plus got donated from the HCl onto the water and that created the hydronium, yeah? So water has effectively there, in simple terms here, it has taken the H plus, yeah? It has accepted the H plus. So therefore, that makes it a base, yeah? However, when a base is added to water, like NH3, water acts as an acid and it donates a H from water onto NH3, so that becomes NH4 plus. So there you go. That's just a little piece of information there. So if you look at water inside a glass here and you look at some water and you're like, that's some nice water there inside that glass, in the plastic cup for whatever at a function, at wherever you are, yeah. That water is not just water, obviously, yeah. It's actually dissociating as we speak, yeah. So what's happening is, by the way, this double thing means a half arrow, yeah, like equilibrium, yeah. Alright, calm. So what's happening is water is actually breaking down into H plus and OH minus, yeah. And again, I said that H plus never exists on its own in water. It always attaches to H2O. So this H plus will then go on to attach to the rest of the water that's in the cup and make H3O plus. So the overall equation we can write for this is that water in a cup is equilibrium, so half equation, reversible reaction, into H hydronium ions and OH minus ions, yeah? OH minus is from up here, from when water dissociated, and then H plus is from when it rejoined back to water. So if you think about this, yeah, this is obviously very like little dissociation. There's not much dissociation here. So that's why like the concentration of water in a cup, a lot of it is water. Only a small amount of it is hydronium ions and OH minus, yeah. That makes sense in it. Most of the cup is actually water, yeah. Calm. So this is very weakly dissociating. So now let's talk about the ionic product of water, yeah? So because water dissociates so weakly, yeah, there's a lot more water molecules compared to H plus and OH minus in a glass, yeah? So if we just go back to this first equation, for example, forget about the other two, just this first one, yeah? It's dissociating very weakly. So there's a lot of H2O still in the glass and there's barely any like H plus and OH minus, yeah? So because of that, yeah, we can effectively say the concentration of water is effectively constant. You understand? So the concentration of actual water it's basically not even changing. It's not, we can assume that it's not even dissociating, basically. You get it? Because of how little it is actually dissociating, yeah? You can think about the concentration of H plus and OH minus is going to be so small compared to H2O that H2O is basically not even dissociating at that point. And because of that, obviously, we can write an equilibrium equation because it's an equilibrium. We say H2O is in reversible reaction with H plus OH minus, and we can create Kc for that equilibrium constant, yeah, as we normally do. You just put the concentration of the products, yeah, over the concentration of the reactant, yeah. So just put the concentration of the product over reactant, we get Kc. Now, because the concentration of water is effectively constant, yeah, what we can do is we can Kc, remember, is also constant. It's the equilibrium constant, right? So therefore, if I've just got a number here as Kc, yeah, and H2O is a constant, it doesn't change. Again, that's going to be a number. I can times H2O concentration up there. So it becomes Kc times H2O is equal to H plus times OH minus, yeah? And because H2O is a constant, yeah, the concentration of H2O is constant, and because the Kc is constant, that just becomes a whole new constant. And so I can call it constant Kw. And so Kw is equal to the concentration of H plus times the concentration of OH minus. And so this is obviously going to be affected by temperature. Reason being is because H2O concentration is always constant relative to these lot. Obviously, you can have different volumes, but relative, yeah, because it's going to cancel anyway. And then obviously, you know that Kc equilibrium constant from previous chapters here, you know that it only gets affected by temperature in it. So therefore, Kw will also be constant unless the temperature changes, yeah, because A would have Kc would have changed, yeah. So obviously Kw is 1 times 10 to the power minus 14, yeah, mole squared dm minus 6, yeah, at 25 degrees Celsius, yeah, and obviously this value will change if the temperature has changed, yeah. Calm. So let's look at pure water then, yeah, pure water. Pure water is the easiest equations here. So let's look at pure water. By the way, for these equations here, acid and base equations are blessed, fam. Like, you actually need to pattern it, I can't lie. If your grades are dead here, and if you can't do acid and base calculations, you need this video, man. You need to pattern that, bro, because that's easy marks. That's 3 marks, like, you know what I'm saying? Alright, calm. H2O, yeah, it gets associated into H plus and OH minus, yeah, as we've already established, yeah. So because water, in pure water, like just pure water, that water, the distilled water, the pure water you got in the lab that you steal and you go spray at all your brethren there, that water there, yeah, it's as dissociating in equal amounts because if you think about it, there's no impurities here. So therefore, it's going to dissociate equally between H plus and OH minus, yeah? So therefore, what I can say is that if it's being split in half, if you think about it, it's being split into H plus and OH minus, yeah? If it's being split in equal amounts because it's pure, the concentration of H plus is going to be the same as the concentration of OH minus, yeah? Because it's being split in equal amounts. So therefore, what I can say is I can take the ionic product of water from earlier, this Kw is equal to H plus times OH minus, and I can replace OH minus with H plus because they're the same concentration. And then it becomes H plus times H plus, which is H plus squared, yeah? So I can say that Kw for pure water is equal to H plus squared, yeah? Come on. pH, yeah, pH is just a logarithmic scale of H plus ion concentration. So obviously you're gonna have proton concentration H plus, and that's gonna tell you something's acidic or basic, obviously, yeah. And so what pH is just a way to like obviously if you look at the H plus concentration, it's gonna be like 1 times 10 to the power of minus whatever the hell, yeah. So obviously if you wanna like get that into like a normal reasonable number, you take minus log 10 of that, and that's gonna make it into a logarithmic scale. So then you'll get a normal number like 3 or 4 or 5 that you can read. Obviously, pH being below 7 is acidic, and above 7 is basic, obviously, yeah. So yeah, this is the equation for pH if you don't know it. Minus log 10 of H plus ion concentration, yeah. So calculate pH of a strong acid here. So this is gonna be the calculations here. So you need to pay strong attention to this, yeah. So let's look at strong acids here. And strong acids, you got two types. You got monoprotic here, and you got diprotic. Let's look at monoprotic first. So monoprotic acids here will only produce 1 mole of H plus ions for every mole of acid. So it's a 1-to-1 ratio between the acid and the H plus ions. So what that means is that the concentration of acid is equal to the concentration of H plus, okay? So for example, let's look at HCl or HNO3. If you want to find the pH of 0.5 concentration of HCl, let's say, what I can say is that the concentration of HCl is the same as the concentration of H plus, yeah? And since the concentration of HCl from the question is 0.5, that means that the concentration of H plus is 0.5. And then use the pH equation of minus log 10 of concentration of H plus here to do minus log 10 of 0.5, which is the concentration of H plus, and you're gonna get 0.3. Obviously, that's a very strong acid here. So that's how you do it. So that's how you do this pH of strong acid and monoprotic acid here. Cool. Let's look at pH of a strong acid for diprotic, yeah? So like H2SO4, yeah? So if you think about it, every molecule of H2SO4 that dissociates you're going to get two hydrogens because you've got two hydrogens being contained here. Yeah? So therefore, 2 moles of H plus ions are produced for every mole of acid here. Hence, the concentration of H plus equals 2 times the concentration of acid. So if I want to get the concentration of H plus to find the pH, you need to times the concentration of acid by 2. So for example, if I want to find the pH of 0.1 concentration sulfuric acid, I can say that concentration of H2SO4 is equal to 2 times concentration of H plus. So therefore, I don't mean it's equal like that. I mean as in I need to times it by 2. That's what I meant in it. So H plus is equal to 0.1 times 2 equals 0.2. The 2 actually should be on the other side effectively. But you get the point in it. The point is that I'm saying that you need to times the concentration of acid by 2. Yeah? And that's going to give you 0.2. And then you're going to take minus log 10 of 0.2 to get the pH, which is 0.7. Again, this is a strong acid, so it's expected, yeah? Calculating the pH of a strong base, yeah? So the concentration of the base here is equal to the concentration of OH minus, yeah? So again, bases, yeah? Strong bases contain that OH minus. So let's look at NaOH, for example, yeah? They have that OH minus and it's dissociating. So NaOH is going into Na plus and OH minus. So what I can assume is I can assume that the concentration of NaOH is the same as the concentration of OH minus ions, okay? So for most bases, one mole of base will dissociate to produce one mole of OH minus, yeah? So then once you know the concentration of OH minus, which will be the same as the concentration of the strong base here, you can use the ionic product of water and rearrange for H plus. So let's say I had 0.1 mole NaOH. That means I have 0.1 mole concentration, by the way, I'm talking about mole per dm cube of OH minus. And so I can put OH minus here and kW will be 1 times 10 to the power minus 14 or whatever, or yeah, that's what it's going to be. And then I just rearrange for H plus in it, so divide by OH minus concentration, we're going to get concentration of H plus, and then just do minus log 10, yeah? So here you've got an example actually. So NaOH concentration is equal to OH minus, so let's say it says find the pH of 0.1 concentration NaOH, so that's going to be 0.1, as you see there, rearrange for H plus here, and put kW 1 times 10 to the power minus 14 over 0.1, you get 1 times 10 to the power minus 13, do minus log 10 of that to find the pH, because that's the hydrogen ion concentration, and you get 13, yeah? So obviously that makes sense. Obviously NaOH is a strong base, so it's going to be close to pH 14, yeah? Calm. Calculating the pH of a weak base, yeah? So, weak acid, sorry, yeah? So, because weak acids don't really dissociate that much, yeah? You can't just assume that the concentration of acid is equal to the concentration of H plus, yeah? For HCl, you could do that, because you can assume that's all basically going to dissociate, yeah? But for weak acids, it barely dissociates, so therefore not a lot of H plus is being produced, so you can't just say they're the same, because the concentrations are definitely not the same, yeah? So hence you need to use equilibrium constant, since this is an equilibrium equation, it's a reversible reaction, yeah? So because only a small amount of acid dissociates, you can assume that the concentration of acid at the start of the reaction is the same as at the end. So you can assume that, let's say a weak acid like ethanoic acid, yeah? The concentration of ethanoic acid at the start is the same as at the end because not that much H plus got broken off from it. You get. So and also you can assume that the dissociation of acid is more than the dissociation of water. Yeah. So any water inside of there, water is also not really dissociating. Yeah. Let's be real. Yeah. So what you can do is you can say that the H plus is actually coming from the acid itself. Yeah. The H pluses are not coming from the water. That's kind of unimportant. That just means you can discard the factor of water that's dissociated. That's obvious, isn't it? You get me? So what we can do here, trust me, this becomes very simple, is because we said that the H plus is not coming from the water, it's coming from the acid, right? When the acid dissociates here, we can say that any concentration of H plus here is equal to the concentration of A minus here, because you know AH, the acid AH, is going to dissociate into H plus and A minus. So therefore, if all the H plus are coming from the acid, the concentration of acid of H plus must be equal to the concentration of the A minus, the conjugate, yeah? So therefore, I can write a Ka expression, obviously, as normal, where I can say, obviously, this is from equilibrium, by the way, yeah? So obviously, we've got AH is equal to H plus plus A minus, yeah? So put the products on the bottom and put the reactant on the top. And now, because I can say that H plus is equal to A minus here, that means that I can replace A minus here with just H plus. And then it becomes H plus times H plus, which becomes H plus squared. So hence, because of that, this is how you calculate the pH of a weak acid here. You use this equation here. Ka, the acid constant here, is going to be equal to H plus squared over the original amount of acid, concentration of acid at the start of the equation. Yeah. So you just take the concentration of acid that they give you. You take the concentration of you take Ka, yeah, and then you rearrange to find H plus. So you times that up there, then you square root, and then you just do minus log 10 of that to give you the pH. Yeah. Okay, let's look at pKa. Yeah. So whenever you see this P thing like pH, pKa, it's just it means you just took a logarithm of it. So you just did minus log 10 of it, yeah? So pH is minus log 10 of H. pKa is minus log 10 of Ka. And it's just another way to basically show you how strong an acid is in it. So if it's a lower value, it means the acid is stronger. So pKa is just P of Ka. So it's just minus log 10 of Ka, yeah? Of acid constant, yeah? So, and that means obviously Ka is equal to 10 to the power of minus pKa. If you don't know how this second thing came, just memorize it, that these are the two formulas. You want pK, you have that. You want Ka, you got the second equation, yeah? But obviously this comes from logs in it. If you do maths, A-level maths, say you know about this. This is the inverse of a log in it. Alright, calm. So this is a little summary here, yeah, of what you do basically for each one for calculations here. So strong acid you see is a monoprotic or diprotic here. And then if it's monoprotic, the concentration of acid is the same as concentration of H plus, then you just do minus log 10. If diprotic, it means you times concentration of acid by 2 to get concentration of H plus. If it's a weak acid here, then you use this equation here, Ka is equal to H plus squared over Ha. And if it's a strong base, you just use Kw is equal to H plus OH minus, find OH minus, and then rearrange for H plus here. Calm. Titrations here. Titrations here, they will be an acid or base in the burette, yeah? So this thing here is called a burette. And the reason you use a burette, yeah, and not like a pipette, is that you can add variable amounts. Obviously, you see this thing here, I can twist that and I can decide how much man's gonna add each time, yeah? Whereas with like a pipette, you squeeze it and it's gonna be a constant amount coming out every time. Obviously, that it matters on your duration, but like you can't, there's a low degree of accuracy there, yeah? So how this works basically is there's an acid or a base inside the burette, yeah? And that acid or base in the burette, let's just say acid for example, yeah? There's acid in the burette that has a known concentration, okay? And there's a base inside the conical flask here that has an unknown concentration, but we know the volume. And we want to find the concentration of that base inside the conical flask. So we're going to have to add a certain amount of acid that we don't know yet. And once we add that acid, we'll read the volume, yeah? And therefore, we will know the concentration of that acid. We'll know the volume of the acid now. And that allows you to calculate using very simple equations like concentration in moles and volume. That allows you to calculate the concentration of the conical flask solution, yeah? So that's just easy, like GCSE type equations, yeah? So you will then add the chemical that's in the burette into the conical flask, yeah? The conical flask has an acid or base with an unknown concentration, unknown volume, yeah? The conical flask also contains some indicator. The reason there's indicator there is because when you add enough acid to neutralize this base, you need a way of knowing that it's been neutralized. So that's why you got a little bit of indicator, yeah, that will tell you that okay, that's it, it's been neutralized. So that's the volume of acid you need to record. That's the amount of acid it took to neutralize it, yeah. So calm. Once enough chemical is added from the burette to the flask, a color change will appear. This is known as the endpoint. So that's where neutralization occurs, yeah. It is important you add the chemical dropwise from the burette near the endpoint to not miss it. So you can kind of tell that nothing's gonna happen at the start. So you can add a decent amount, but don't risk it too much. And then when it happens like near the thing, you need the exact volume at which like it neutralizes. So you need to add it like drop by drop in it. And one of those drops will add it and you'll see the indicator come out. You get me? So you would then read how much the volume from the burette was needed, yes, to neutralize the chemical in the flask. This way you have known concentration and volume, and so this allows you to find the concentration of the chemical in the flask, yeah? And obviously you need to read from the bottom of the meniscus, yeah? So this thing here is called the meniscus. You need to read from the bottom and make sure you read at eye level, yeah? As you see, this brother here, he's reading it from the bottom, yeah? Because he's the bottom kind of guy. And he's reading it at 19.62. This brother's reading it from up here, and he's seeing it at 19.42, fam, yeah? So obviously read at eye level so you get the accurate reading, yeah? And that's also what you can waffle about in your paper. Titrations, you should record the volume to 2 decimal places, yeah, and you should repeat until you have two concordant results, yeah. So this means that are within 0.1 centimeter, yeah. So concordant means 0.1. So for example, that would be repeat 2 and repeat 3, or it could be repeat 1 and repeat 2. And so then what you can do here is you can calculate the mean titer, yeah, the mean volume. Titration curves. Titration curves are pretty self-explanatory. They're not too difficult, yeah. So effectively, what it means is that, let's say for example, let's look at the first one. So strong acid and strong base. Yeah, you've got a strong acid inside that conical flask. Yeah, as you see by the fact that is a scale of pH, by the way, on the left. And so as you see, yeah, the pH is like 1.5. Yeah, so you've got a very strong acid in the conical flask. Yeah, and then as you add the base from the burette into the flask. Yeah, the pH is slowly going to increase because you're mixing with base. And then at this point here, the equivalence point is going to neutralize, and that's when it shoots up all the way there. And the pH changes because it's going to go neutral, and then you've got the excess base that's added now. So it's going to become very basic. And because it's a strong acid and you're adding a strong base here, it will start very low because it's strong acid, and it will end very high because it's strong base. And this equivalence point will be stretched across. So you need to kind of understand these titration curves and know them. Yeah, just because it'll come up in questions, maybe more multiple choice or something. But obviously, yeah, the main thing here is it's not, you don't need to memorize it. Like this is just logical, innit? So like strong acid and weak base, again, you're starting at a very strong point down here, and because it's a weak base, it's not really gonna end at a very high pH because it's a weak base. It's not that basic, so it's not gonna be as strong high up as the strong base, yeah. And because of that, you're getting a small equivalence point. You get weak acid and weak base. That's actually wrong, you know. They're trying to finesse man out here, yeah. Telling you, mate, you can't trust these brothers, yeah. Listen, this one out over here, we're not taking this out. I'm leaving this in here. Listen, yeah. This diagram in the top right, yeah, corner, that's weak acid, weak base, yeah. Because this is a weak acid, yeah. This is strong acid, strong base in the bottom left, yeah. So this is strong acid, strong base. You're starting at a very strong acid down here, and you're ending at a very weak base up there, and so you get okay equivalence point. This is a weak acid, weak base in the top right, where you're starting at a weak acid and you're ending at a weak base. You're getting a very short equivalence point, yeah. And then the one in the bottom right is obviously weak acid, strong base. This is very self-explanatory. You're starting at a weak acid, so a bit high up here, and you're ending at a strong base, so very high up. That's all this is here. Calm. So that's called the equivalence point, as I spoke before. And this before it is called the buffered region, yeah. So this is showing buffer action, can show that. It's also showing the fact that like you're adding if you think about it, the pH, let's say if you have acid, right, the pH is going to be very low, and then you're kind of buffering it in a way because you're adding that a higher pH, you're adding a base to it. And so that's why it's kind of moving. That's why it's very steep at the start. That's why it's kind of being buffered a little bit there, as you see, and then it shoots up here. So always when you draw titration curves, yeah, this is a pro tip here. Always you have to draw it like very steep at the start, yeah. So make sure you do that. Make sure you do it steep at the start and then show how it like buffers a little bit, yeah. Alright, calm. So so that's the equivalence point, yeah. And then this here, so this is halfway between the start and the end point, the equivalence point. This is called the half equivalence point or half neutralization point. That point there, yeah, is basically the point where half of the acid has been neutralized, yeah. So half of the acid has been neutralized by the base, and half of the acid is still remaining, yeah. And what's important at this point here is that pH, basically the reason you can find this one here is if you want to find the pH of the acid here of the situation there, you just need to do P of Ka. So I'll explain why there. If you think about it, yeah, Ha is being broken up into A minus and H plus, and at this point, yeah, because half of the acid has been neutralized, half of Ha has been turned into A minus, yeah? So therefore, I can say that the concentration of Ha is equal to the concentration of A minus, yeah? So if you look at the Ka expression, yeah, because obviously product over reactant, yeah, A minus and Ha cancel, yeah, because they both have the same concentration at that point. So therefore, Ka is just equal to H plus. So if Ka is equal to H plus here, I can therefore just do minus log 10 of both sides, and therefore minus log 10 of Ka is pKa, and minus log 10 of H plus is pH. So that's it, very simple. Calm. So as you see here, because of this equivalence point bullshit here, you need to choose like a correct indicator that changes color in that pH range. Yeah, if you've got an indicator that works down at like pH 2, then it's not gonna change color up there in the equivalence point when you actually need it. So you need to provide an accurate one. Yeah, and so these are the indicators here. You should learn them. The litmus paper is kind of irrelevant. Don't worry about that. But mainly the methyl orange and the phenolphthalein or whatever it's called. Yeah, so methyl orange and the phenolphthalein. Yeah, those two are the important ones. Yeah, so methyl orange has a pH color at like a more of acidic one, 3 to 5, and it's going to be red at first, and then it will turn yellow. So if it's acidic, it will be red. If it's basic, the indicator will turn yellow. Yeah, and this is the most used one, really and truly. I think that they do in schools. Yeah, is phenolphthalein. Yeah, um, that's got a more basic pH change. Yeah, so 8 to 10. Yeah, so within that range, if the equivalence point is within that range, you use phenolphthalein. Yeah, and this one goes from colorless to pink. Yeah, I think that's more common. Yeah, like you probably done it in school or something. You got like the colorless thing. You put like that in and it turns pink or something. I don't know. Yeah, so there you go. So just memorize these two indicators. Yeah, and the situation. And litmus is a bit between that. Obviously, it just goes from red to blue. That's standard. We know that. So yeah, this is another example. As you see for this one, yeah, the pH is actually starting up here and ending down there. The reason for that is just because it's the opposite way. You can also see titration curves the opposite way, right? So instead of having acid in the burette and having a base in the conical flask, I mean base in the burette and acid in the conical flask, this is the opposite. So you got acid in the burette and you're starting with base in the conical flask, yeah? So because you're starting with a base in the conical flask, you're starting at high pH, and as you add acid from the burette to titrate it, you obviously the pH is gonna go down. And obviously this is a strong base and it's ending at a strong acid here. So phenolphthalein will work in that kind of range here, and methyl orange will work in that kind of range down there, yeah. However, for weak acid and weak base, yeah, titrations, as you saw the one in the top right, yeah, of those four images, yeah, there's a very short like equivalence point. So therefore you can't even judge it, yeah. So therefore you need to use a pH meter, yeah, as it isn't a sharp enough pH change to show like for an indicator to actually work, yeah. Because it's so tight, there's no way an indicator is gonna work. So you need to use a pH meter, yeah. Or they call it pH probe as well. Alright, diprotic acids, yeah. Listen, fam. The things on top of the thing. It doesn't matter, yeah. It doesn't even matter, yeah. Allow it. Yeah. Acids like fendoic acid are diprotic here, meaning they release two protons when ionized. So effectively, yeah, you've got the acid here, yeah, and it's got two protons that it contains. And so what's gonna happen is the OH is gonna neutralize the first proton, yeah. It's gonna combine OH is gonna combine to H plus to neutralize the first proton, and that's what you're getting over here, this equivalence point. And then there's still gonna be that H left, so it's still very acidic because fendoic acid still has another proton to spare, yeah. And then obviously the OH minus, the base is going to react with that proton again to fully neutralize it. That's the second equivalence point there, and it comes up there. This is irrelevant anyway, but this is what a titration curve looks like for a diprotic acid. Buffers, yeah, buffer solutions, yeah. So buffers are chemicals that resist pH when a small amount of acid or base is added, yeah. So when you add a small amount of acid or base, it will resist it, yeah. It's important that you don't say that it stops it, it just resists it, yeah. Calm. So acidic buffers, yeah. So you need to understand the dynamics behind buffers, yeah? So acidic buffers will resist pH change to make sure the pH remains below pH, yeah? So below pH 7, yeah? So that's what acidic buffers will do. They'll resist the pH change to make sure that the solution stays acidic. That makes sense, yeah? And they're always made from a weak acid and its salt. So if I look at an acidic buffer, obviously weak acid, ethanoic acid here, is obviously going into CH3COO minus and H plus. And the conjugate salt to ethanoic acid is CH3COONA. And this is actually strongly dissociating, yeah, CH3COONA will dissociate very readily into CH3COO minus and Na plus. So that's why I've shown this as a strong arrow, and the top one is just a half arrow, yeah. So these are the two compounds you've got in a buffer. This is what an acidic buffer actually is, yeah, is these two things. And these equations are coexisting in that flask, yeah, and they're working together. And you'll see why in a minute. So let's say that I'm gonna add H plus to an acidic buffer, yeah? So we've got an acidic buffer and we're adding acid to it, yeah? Well, the acid, the H plus, is gonna react with CH3COO. So it's gonna react with this over here, as you see that. And because of that, what are you going to produce? You're going to produce CH3COOH, yeah? And hence equilibrium will shift to the left. So what do I mean by the left? You're going to say, what do you mean by the left? Is shifting to CHCNOONA? No, I said these equations coexisting in it. So therefore it's going to shift down to the left here to CH3COOH, and it's going to produce more acid. And so that counteracts the effect of adding that extra acid into there. It's going to produce more CHCOOH, yeah, and it's going to reduce the concentration of CH3COO minus, yeah. You'll see how this becomes relevant later in certain questions, yeah, in buffer calculations, yeah. Adding OH to an acidic buffer. So let's look now, adding a base to a buffer, yeah? So as you know, if you add a base to an acidic buffer, the acidic buffer is going to counteract it, yeah? To keep the pH below 7, yeah? To keep it acidic. So let's see how that actually works, yeah? So the OH minus from the base is going to react with the H plus. So it's going to react with the H plus over here. And when it reacts with the H plus here, you're going to be creating CH3CO minus, yeah? And so therefore, because you're using up the H plus ion there, because this is an equilibrium, due to Le Chatelet's principle, the equilibrium is going to shift to the right again to replenish the H plus, and that's going to make it acidic again. So do you see that? So the OH is going to react with the H plus, equilibrium is going to shift to the right to replenish those lost H pluses, and that's how the buffer's working. Do you get that situation there, yeah? That's how this works. And you might also ask, why does the H plus not react with Na plus? What am I even talking about? I'm waffling in there. I meant, why does the OH minus that you added the base, why does that not react with the Na plus? That's what I was trying to say. Well, if you think about it, if it does that, that will create NaOH, yeah? And NaOH is what? It's a strong base, yeah? So therefore it's just gonna dissociate straight away anyway back into OH minus. So that's why it's pointless. It mainly reacts with the H plus, yeah? Calm. So it's gonna react with that H plus, and because you're decreasing that concentration of H plus, Le Chatelet's principle will make more of the forward reaction, it will shift to the right. Calm. Basic buffers, yeah. So basic buffers will resist the pH to keep it above pH 7, yeah. So to keep the conditions basic, yeah. And so they're actually made from a weak base and its salt, yeah. So same way how we had a weak acid and its salt, we've got a weak base and its salt. So like ammonia here is a weak base. I said earlier, it doesn't even have a hydroxide group. And the salt for ammonia will be this ammonium chloride, yeah, NH4Cl. And again, same situation. You've got high concentration of NH3, high concentration of water, and you're not really dissociating much, not really reacting. So therefore you got low concentration NH4 plus and low concentration OH minus here. So that's what this equilibrium indicates here. And here you got strong forward reaction. Yeah, you got NH4Cl minus the basic salt, the salt here will be again dissociating readily, yeah, very fast. It will always be dissociating and will dissociate strongly into NH4 plus and Cl minus here. And again, so in a basic buffer, you got these two equations that are coexisting, yeah. You got these two compounds inside that buffer. So let's see. So let's add OH minus. Let's add a base into the basic buffer, yeah. So the OH minus will react with NH4 plus, yeah. And when it reacts with NH4 plus, the equilibrium will again, so it's gonna react with this NH4 plus down here, and that's gonna again shift equilibrium to the left to produce more yeah, to produce more NH3 or whatever, and H2O. So as you see, it's just the inverse of this reaction. So OH minus is effectively reacting with NH4, and it's just going to shift equilibrium to the left, yeah? So again, nothing's really happening there when you add a basic buffer. The important thing you need to note here is that if you do have a buffer calculation and you add a OH minus, you add a base to it, you need to increase the moles of NH3 because think about it, we're making more NH3 and you need to decrease the moles of NH4 because that's what's reacting with. So we're going to decrease the moles of NH4, yeah? So by the however much moles of base was added, yeah, you need to increase the moles of NH3 and decrease moles of NH4. Same with the adding H plus to an acidic buffer as well. If you add an acid to an acidic buffer, yeah, it's the same situation. You need to increase the moles of the acid and decrease the moles of that conjugate thing here. You get me? Cool. You'll see in the questions anyway. Adding H plus to a basic buffer, yeah. So again, so if I've got a basic buffer and I'm adding an acid to it, it's gonna have to counteract that, yeah, to bring the pH above, to keep it above 7, yeah, keep it basic conditions, yeah. So again, same thing, yeah. H plus is gonna react with OH minus, yeah. It's gonna react with OH minus, yeah. And because of that, we don't have any OH minus anymore. So again, the Chatelet principle is gonna equilibrium is gonna shift to the right again to produce more OH minus to replenish that OH minus and increase the pH again. You get it? And again, OH could H plus when you add an acid to it, it could react with the Cl minus. But what's that gonna do? It's gonna make HCl, and HCl is just a strong acid, so it's gonna readily dissociate anyway back into H plus and Cl minus. So it's pointless, yeah. So that's how buffers work, yeah. Let's look at buffer calculations then, yeah? So buffer calculations are probably the hardest part of this topic, I'll be real. The other calculations over there, the acids and bases and that's kind of calm once you pattern it, once you do a couple of questions here. Buffer calculations can get a bit tricky. So let's see what I'm going with buffer calculations here. You get three types here, three types. Two main types and a kind of like an addition. You get buffer calculation of just like a acid and a salt, yeah? So that's just calculate the pH of a buffer solution that has the acid and it has the salt of the acid, right? Then you get calculate the buffer calculation of acid and like a base, yeah. And then you also get the buffer calculations where you're like adding like an acid to an acid or a base to a base. You get me? So you're adding an acid to an acidic buffer or you're adding a base to a basic buffer, yeah. And the one in, yeah, so let's start with this one, yeah. So buffer calculation of acid and and a salt, yeah. So calculate the pH of a buffer solution that contains 0.03 moles of ethanoic acid and 0.025 moles of sodium ethanoate in a 1 decimeter cubed solution. The value of Ka for ethanoic acid at 25 degrees is that. So, as you know, the ethanoic acid is just dissociating into the ethanoate ions and H plus, yeah? And hence, Ka, I can write a K expression for that, is equal to CH3COO minus times H plus over CH3COOH, yeah? Calm. So that's just a standard Ka expression, yeah? Now, because weak acids barely dissociate, so remember the acidic buffer is made of a weak acid and it's salt. So because weak acids don't really dissociate much, I can assume that you see the CH3COO minus. I can assume that's not coming really from the CH3COOH. Only a small amount is being produced. I'm assuming that most of that ethanoate ion is coming from the sodium ethanoate. Yeah, because as I said earlier, the salt strongly dissociates. Yeah, so all that ethanoate ions is actually coming from sodium ethanoate. So therefore, what I can say is that the concentration of the salt is actually equal to the A minus is equal to the ethanoate ions. Yeah, so hence, therefore, if I want to find the concentration of CH3COO minus, so I can use it in the Ka expression, it's actually this moles up here of sodium ethanoate of the salt. Yeah, so remember that when you do the calculation. So therefore, that's going to be 0.025. I know I said concentration, I'm using moles here, but it's because it's in a 1 decimeter cube solution, so we're dividing it by 1 anyway, so it's pointless. Come. Then just rearrange for H plus. So as you saw the K expression, rearrange for H plus times K up there, times the thing up there, divide by CH3COO minus. And now just plug in all the numbers, bro. You've got Ka from here. You've got 0.03, which is the moles of ethanoic acid at the start, yeah, as we talked about. And then you've got 0.025 of the sodium ethanoate, which is the equal to the ethanoate ions concentration. So then just put that all together, you get the H plus concentration, and then you're just gonna do minus log 10 of that to get the pH. So minus log 10 of that gives you the pH of 4.68. Obviously, this is an acidic buffer, so obviously that makes sense. Calm fam. Let's look at another one, yeah? So let's look at a buffer calculation with an acid and a base here. So this is like either, this can be in two ways. It can either be like an acidic buffer, and then you're adding like a base into it, or it can be an acidic buffer. I kind of said the same thing, but like an acid, it could be like an acid and you're adding base to that to make a buffer like that. It can be in those kind of ways. So they both follow the same basis. So in a buffer solution, yeah, the concentration of ethanoic acid is whatever. Let's just skip that waffle. So how do we actually do this? Well, effectively, what you're going on here, yeah, is you got ethanoic acid, and you got the ethanoate ions, obviously, because it's a buffer, yeah. So you got the ethanoic acid and you got a salt, yeah. And now what you're doing is you're adding a strong base like sodium hydroxide. You're adding sodium hydroxide into the buffer. So you're adding that into the buffer. And now you want to find the pH of the solution after you've added all the sodium hydroxide. So how do we do that? How do we do that? Well, let's just find the moles of everything beforehand. So the moles of ethanoic acid is just going to be equal to the concentration 0.260 times the volume, yeah, which was it said introduced into 500 centimeter cube, yeah, so calm. Safe. So now, what you want to do now is, and that gives you 0.13 moles, yeah, of ethanoic acid. Then find the moles of sodium ethanoate, or ethanoate ions, yeah. So ethanoate ions is that concentration, and so you just times that by the volume, you get the moles of ethanoate. And now, let's think about what's going to happen when we add that, add the OH minus to it. We add the sodium hydroxide. Remember these two equations from earlier. And I said, yeah, if I add sodium hydroxide, it's going to react with H plus, and hence the equilibrium is going to shift to the right to replenish the H plus. So hence, the concentration of ethanoic acid is going to decrease, and the concentration of stuff on the right is going to increase to keep that buffer. So hence, CH3COO minus is going to increase by the same amount of moles as the sodium hydroxide, and the CH3COOH is going to decrease by the same amount of moles of sodium hydroxide. Does that make sense? So the new moles, so the moles of ethanoic acid after, is going to be equal to the moles I had before, take away the moles of sodium hydroxide, and that's going to give you 0.123 moles. And again, the moles of ethanol ions after is going to be the moles before, adding that sodium hydroxide moles to get the ones after. So does that make sense? Yeah. When you add NaOH or OH minus ions, it's going to react with this H plus, and as a result, to replenish that, equilibrium is going to shift to the right. So you're going to produce more CH3CO minus, and you're going to decrease CH3COOH. You get it? So calm. Now you've got the concentrations, just rearrange for H plus using the K expression. You've got Ka here, and you've got the new moles of ethanoic acid, and you've got the new moles of ethanoate ions. Just put it all together, you get the H plus concentration. Do minus log 10 of that, and again, it's gonna be like it's gonna be buffered in it, so it's gonna resist the NaOH solution here. So therefore, it's gonna stay acidic here at 4.5. Come on. Buffer calculations with adding an acid here. So this is the final situation. So let's say I've got a buffer and I add some more acid to that. Why not, fam? You get me? Yeah. Then again, this is why you have to understand those equations I was talking about earlier of how buffers work, so you can easily think of this part. You can also just memorize it like it's minor. Yeah. So let's think about this here. We've got an acid of we've got an acid of propanoic acid and its salt, and then we're gonna add a strong acid H2O to that, HCl to that. So Wagwan, what are we gonna do now? So let's find the moles of propanoic acid first. Yeah, so take the concentration of propanoic acid here, which is 0.15, times that by 500 over 1,000. Obviously, that's the volume into decimeter, and that's gonna give you the moles. Yeah, and then again, sodium propanoate, do the same thing. Find the moles of that is 0.025, and then find the moles of HCl that you added. Yeah, so because it was 2 mole per dm cubed of HCl, uh, and you're adding that to the 1,000 situation. I mean, sorry, it's 5 centimeter cubed of that. So change that into decimeter. So divide by 1,000 and times by 2, you get 0.01 moles of HCl. And so now again, as I said earlier, when you add HCl, the H plus ions are going to react with the A minus ions. Remember, the propanoic acid is dissociating into H plus and propanoate ions, right? And the second equation, the sodium propanoate, is dissociating into propanoate ions and sodium. So again, as I said, the H plus is going to react with that propanoate ions to create more sodium, to create more propanoic acid. So therefore, the propanoic acid concentration is going to increase by the same amount of moles as HCl. So hence, the new moles of propanoic acid is going to be the original moles plus 0.01, which is going to give you that. Ethanoate, obviously, I realize now that's not 25, it's 75, obviously, because it's the same concentrations. Calm. Ethanoate is going to decrease because that's what's reacting with, that's what the H plus is reacting with, so we're taking away ethanoate, and that's going to be the original moles of ethanoate ions minus 0.01, and that's the new moles here. And now, just put it into the equation here, so you've got H plus is equal to Ka times AH over A minus. Also, by the way, because you added 5 centimeter cube of HCl to 500 centimeter cube of buffer, you also need to change the volume. The volume is not 500 anymore, it's 505 now. But shit should cancel anyway, so I don't think it's really relevant. So yeah, and then just rearrange for H plus and then just solve it. Just do minus log 10 of H plus and you get the pH. Finally, let's look at some use of buffers. So shampoo has an acidic buffer to stop alkalinity, because like if you're, you can't let this solution become alkaline and put it in your hair, otherwise you'll dry out your hair. So have an acidic buffer to make sure that it stays slightly acidic, perfect for your hair. Drinks, they contain acidic buffers here to ensure the taste maintains consistent, because if the pH changes, the taste can also change. Yeah. And then obviously blood, like obviously it's important to keep it at pH 7.4 when it's being transmitted, obviously for reasons, of course, like you've got enzymes, you've got whatever, you've got all that stuff in there, you need to keep that at a certain level. Yeah. And that's it really. Nice little easy topic here. Hopefully that patterns it.